Hello everyone, my name is Minghao Liu from Institute of Software, Chinese Academy of Sciences. Here I will give a brief introduction of my work, learning the satisfiability of pseudo-Boolean problem with graph neural networks. As we know, many effective heuristics in solving constraint satisfaction problems rely on the observation and idea from human experts. The deep learning systems have improved the state-of-the-art standards of many AI tasks across domains. This also inspired us to apply learning-based approaches to solve constraint satisfaction problems, which may capture the specific structures of the problem from benchmarks, so that some effective implicit heuristics may be learned automatically. An important question is the choice of model. Compared with convolutional neural network and recurrent neural network, we believe graph neural network is a promising choice. More specifically, we choose to learn the satisfiability of pseudo-Boolean problem. We believe it provides an important setting for investigating the capability of graph neural network in extracting features of CSPs with numerical constraints. Our GNN model contains 4 parts: normalization, graph construction, message passing, and readout. We prepare 2 different pseudo-Boolean problems for the experiments: 0-1 knapsack and weighted independent set. These 2 problems have very different distributions. The model can converge and achieve more than 85% classification accuracy when the number of variables is no larger than 40. From the results, our model is believed to have learned some features related to the satisfiability of problem. Moreover, the accuracy of our model outperforms that of NeuralSet, a GNN model for solving the satisfiability of set formulas in multiple dimensions. So our model can be seen as a generalization of it. We hope the model can provide a basis for a series of future work on learning to solve different CSPs with numerical constraints. If you have any questions, please feel free to contact. Thanks for your attention.
This paper deals with the notion of fairness in machine learning. The context is a classifier. We want to learn a Boolean function which has arguments which are either non-protected or protected. Examples of protected features would be, for example, gender or race. And the idea is we want to learn a function, a classifier, which does not depend on gender or race or other protected features. One concrete example is whether a bank should approve a loan to a customer. We would hope that the model we learn would not take into account gender or race of the client. Before trying to construct a fair model from data, we have to ask certain questions like, what is a criterion for dataset bias, for fairness of a model, or fairness of a particular decision? And then we'll be able to go on to describe how to learn a fair model from possibly biased data. Now, the criterion, which is fairly obvious to decide whether a model is fair or not, is that it is only a function of the non-protected features. So this is called fairness through unawareness. Now we can detect unfairness by exhibiting two examples. For example, Alice and Bob, who are identical in terms of salary, age, etc., with unprotected features, but differ obviously in gender. Alice is refused a loan, but Bob isn't. So we're actually primarily interested in learning fair models from a possibly biased dataset. So in our experimental trials, we used a SAT solver. So the model we're trying to learn is a KDNF, where K is some small constant, which matches as much as possible the data and is 100% fair. And we coded this problem of finding the KDNF as a SAT instance. So the main principle is we impose fairness, and this is necessarily at the cost of accuracy in the case of biased data. We may further sacrifice accuracy in order to obtain a simple model, for example, a KDNF with K small. What I haven't talked about here is the local notion of fairness, the fairness of a particular decision. Now here we actually found two different notions, and we analyze the computational complexity, and here complexity may be an issue. But the main positive point of this paper is that we've shown that it is possible to learn a fair model from possibly biased data. Nonetheless, there is obviously further work required to deal with, for example, correlations between protected and non-protected features, or presence of irrelevant features which can hide dataset bias.
Welcome to our presentation on theoretical and experimental results for planning with learned binarized neural network transition models. My name is Pulsar, and this is a joint work with Joe, Jacob, and Peter. To give a brief overview, I will start with a motivational example that is in the area of planning against adversarial agents. We control an agent whose purpose is to obtain a key to an initially locked door. In this planning problem and the others, we're not going to assume knowledge on the model of the planning problem. Specifically, we're not going to assume that we know what the transition function is. So in this specific example, this corresponds to not knowing where the enemy will move to as a function of our current location and our movement. In order to be able to plan with these learned BNNs, we're going to build on the existing data-driven AI planning formalism, which compiles the learned BNNs across the fixed planning horizon. And in the learned BNNs, let me remind you that the weights and the activation functions are restricted to 1 and -1. Given this formalism, we present new and existing optimization models to plan with these learned neural network models. We will present a 0-1 integer linear programming model and solve it with both branch and bound solvers and off-the-shelf pseudo-Boolean optimization solvers, that is, rounding set. We're going to introduce two new CP models and an existing weighted partial max set model. We proceed by presenting theoretical results on feasible planning with BNNs and show that it's NP complete. We do so by showing that the problem is in NP on a very high level, which corresponds to guessing the values of our actions and performing BNN inference, and showing that the problem is NP hard by reducing 3-set to the learned planning problem. Next, we show how to leverage model symmetry to derive no-goods. Here, we learn symmetrical no-goods from constraints that represent the learned binarized neural network function, lift, and apply it to other time steps. Experimentally, we will show that the PBO model that is solved by rounding set covers the most number of problems in least amount of time. Similarly, the ability to leverage model symmetry can speed up our base encoding from 1 to 3 orders of magnitude. Finally, we will conclude this presentation and present areas for future work.
So welcome to this CP and ML talk. This is joint work with Céline Brouard and Simon de Givry, working with me at INRAE. And Simon and I are also members of this Artificial and Natural Intelligence Toulouse Institute. This talk will be about learning cost-function networks from a set of high-quality solutions. So we essentially start from a training and validation set of high-quality solutions, and we leverage a recent scalable convex optimization algorithm from probabilistic graphical models to learn cost-function networks. And this algorithm is scalable, but it requires to set an hyperparameter lambda, and to tune this hyperparameter, we actually use the validation set. We take the cost function which has been learned by the convex optimization algorithm, and we use solutions from the validation set and a WCSP solver to check if the cost function network is able to produce good solutions in the sense of the validation set. So at the end, you get your cost function network. You can go through an extra optional step, which we call empirical hardening, where some of the cost function will be transformed into constraints, and you have your final learned problem. It is a cost function network. You can scrutinize it, you can add extra constraints if you have exact knowledge to add, and you can refine the criteria using extra cost function. If you stay with us, you will learn how we use graphical models to connect CP with probabilistic machine learning. You will also see how we can avoid this NP-hard loop, avoid spending too much time on it by simple tricks. And then the framework being defined, you will see how it can learn to play the Sudoku without knowing the rules, of course, and even starting from images with handwritten digits, as on the right, and how it compares with recent deep learning friendly architectures that learn to reason on the Sudoku problems. We also tried this on industrial problems. So it's a Renault car configuration problem. You want to learn user preferences and combine them with known configuration constraints to set up a configuration assistant.